We have been talking about some of the problems that we're able to solve with our knowledge of laws created by first Galileo and later refined by Newton. The law that says that objects will continue in their state of motion unless they're acted on by some sort of force to do something else. I want to look now at problems related to this. The first one I want to have a look at is related to the solar system. We know that the Earth and planets move around the Sun. The question is, what force keeps them moving? And it is not inertia. Be very clear about this. Inertia is not a force. Inertia is the property of a body to continue to do what it is doing unless it is acted on by a force. So inertia itself, in fact, is not a force. Let's have a look at a little bit of the detail of this problem. Here we've got the Sun and two of the planets, Mercury and the Earth. And I want to have a look in detail at the motion of these two planets. Let's consider the Earth first. The Earth travels in an almost circular orbit. In fact, it's not a circular orbit. Aristotle believed it was a circular. Copernicus also believed it was a circular orbit, and so too did the Christian Church, because they believed that everything was made perfect by God. In fact, they are almost circular orbits, but they are not quite. They're in fact elliptical orbits, which create some complications which we're going to ignore for this explanation. So we've got the Earth moving around the Sun, this orbit, and we've got the gravitational attraction between the Sun and the Earth, keeping the Earth in its orbit. But the question is not what keeps the Earth in its orbit. The question is what keeps the Earth moving with some velocity around that orbit. Now, I want you to be clear here about the situation that we've got. Here we've got the Earth that's attracted along this red line by the gravitational pull that exists between the Earth and the Sun. The velocity of the Earth, the direction of travel of the Earth, is at what is known as a tangent to this circular line. If suddenly the gravitational force from the Sun stopped, the Earth would follow this green trajectory here. It wouldn't continue to move around in a circle. It wouldn't suddenly fly off in a direction away from the Sun. It would move in the direction that it had. That's according to Newton's first law, the law that was invented by Galileo from his observations about rolling balls down inclines, that objects keep moving unless they're acted on by a force to do something else. Now, what we have here is the Earth moving in this direction. At this particular instant, it's moving in this direction. And so if the gravitational pull of the Sun was to cease at that point, the Earth would continue to move along this green line. This is a simple thing for you to check yourselves. Tie some keys, not very heavy ones, tie some keys to the end of a string and then slowly twirl the keys around in a circular path. Let go of the keys and see which direction they move in. You will see, as in this example here, that just as if it was the gravitational pull of the Sun that ceased to exist, when you let the keys go, the keys will not fly off in a direction away from your hand. They will fly off in a direction tangent to the circle that they were moving in. Now, this is extremely important to understand, because the short answer to the question, what keeps the Earth in motion around the Sun, is that the Sun keeps changing the direction of the Earth. But it does not really change the speed of the Earth. Now, that's not entirely true. As I said earlier, the path of the Earth around the Sun is in fact an ellipse, not a circle. And so the Sun does cause the Earth to speed up a little bit in its orbit, and at other times to slow down a little bit in its orbit. But we're going to ignore those effects because they cancel each other out. It speeds up as much as and we're going to assume that they are in fact circular orbits. And then if that's true, then the attraction of the Sun is always at right angles to the direction of motion. And so the Sun itself does not cause the Earth to go faster or slower. So what created the motion of the Earth around the Sun? Well, it got it from its very first instant of creation. And unless it's acted on by some sort of force to cause it to slow down, it won't. It will keep moving velocity that it had before. Now you might object to that and you might say, well, it is being acted on by a force. It's the force of the Sun and we can't ignore it. And you're right, and it is unbelievably important in understanding this circular motion. Let's have a look at what happens in the case of Mercury, where we can see a bit more of the orbit. In this position, the velocity of Mercury is at a tangent to the circle, so it's off in this direction, the same way as the velocity of the Earth's orbit is at a tangent to the orbit of the Earth. The same thing is true for Mercury, that if the Sun's force stopped at this point and there was no gravitational attraction between the Sun and Mercury, the planet would fly off in a line in this direction. Again, you can check that with your keys. If you let go your keys at the 12 o'clock position as you go around in a circle, which way do they go? Do they fly this direction? Do they fly off in this direction? Do they fly off in this direction? No, you will observe by your own experiments that they fly off in this direction, and that's what would happen with the planet. But of course Mercury doesn't fly off. The gravitational attraction of the Sun, which is directed toward the center of the Sun along this line, the red dotted line between the two, that is pulling Mercury around the Sun, so that instead of allowing Mercury to fly off in the direction that we've shown here, a little bit later what will actually happen is that Mercury will be in this position in its orbit. Now it would have been in a position out here, but the pull of the Sun directly towards the center of the Sun, this gravitational pull of the Sun, this gravitational force of the Sun between the Sun and Mercury, drags Mercury back into this circular path. So the Sun is critical in the orbits of the planets, of course. It's providing the gravitational force which doesn't change the magnitude of the velocity, but it changes the direction of the velocity. Do you remember that we talked about the difference between scalars and vectors, and we gave the example of velocity as a vector quantity. Vector quantities have a size, they have a direction. In what the attraction of the Sun has caused to happen is it has caused the direction of the velocity to change. It has not changed the magnitude, it has changed the direction of the velocity, and in that sense it has changed the velocity of Mercury. It has not, however, changed the speed. The speed remains the same. Now this is really important to understand, and this is one of the reasons that we have vector quantities in physics. The attraction of the Sun, this central attraction of the Sun, is not causing the speed of Mercury to change. That remains the same. It's traveling as fast at this point as it is at this point. But what it is causing to change is the direction of the speed. And in that sense, the Sun is causing the velocity of Mercury to change, but it is not causing the size of the velocity to change. It is only causing the direction of the velocity to change. So, to sum up then, what we have is that the gravitational attraction between the Sun and the planets makes the orbits nearly circular, but not quite. And because of this, the Sun does have an effect on the speeds of the planets as they go around in their orbits, but it causes them to speed up as much as it causes them to slow down, and therefore has no net effect on the speed of the planets that orbit the Sun. However, while the gravitational attraction between the planets and the Sun does not affect the speed, the magnitude of the velocities of the planets around the Sun, it absolutely does affect the direction of the planets. In fact, it is what causes the planets to move in their circular path. It is called a centrally directed force because it acts on the line that directly joins the planets to the Sun. What keeps the Earth and the planets moving at essentially the same speed in their orbits? Nothing does. They are simply obeying the laws that Galileo and Newton discovered governing the motion of objects that we see, which is that unless they are acted on by a force that causes them to change their state of motion, that all objects continue to do what they were doing before the action of any such force. So the effect of the force of gravity in the case of the Sun and the planets is only to change the direction of the velocity. It does not change the size of the velocity, what we call the magnitude of the velocity, what we commonly call the speed. So the short answer is what keeps the Earth and the planets moving at the speeds that they have traveling around the Sun is nothing does. They had those speeds originally and they continue to have those speeds because nothing acts to change them. There is no force causing them to speed up or slow down.